Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 9th grade topic, identifying linear functions. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any question about what we said today, or even your own homework, you can always put it in the comment box below, or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. Today's video is going to have 4 parts, so leave a like, smash the subscribe button, and let's get started. So before we jump into identifying whether our functions are linear or non-linear, we need to first have a working definition. Now, this is especially true for this topic, linear functions, because as you get into higher level maths, you will be faced with different working definitions. And those working definitions will define what a linear function is. And those definitions may disqualify what we're covering today as linear functions. So I don't want you to get confused if you are in some of those higher level maths and you're seeing this and saying this is not a linear function, you're maybe dealing with a different working definition. In order to erase any of that potential confusion, let's make sure we're on the same page, and we're going to define what we're going to consider linear functions for this video. So for this video, a linear function is going to be any function that depicts a straight line when drawn. So if you draw a function, if it is a straight line, that is what we're considering a linear function. So if you have a straight line after you make your function, remember it has to be a function, then we're going to consider that to be a linear function. So for the sake of this video, moving forward, this is what we're talking about when we say, is it linear or non-linear? So there are going to be 3 ways in which you're going to be identifying whether a function is linear or non-linear. The first is by graph, and I think that's the easiest one, so I'm going to start there. The second one is going to be by the actual function, the model representation, and the third is going to be by the values or the points. Now, I personally think that by graph is the easiest because it is purely visual. Remember, our working definition is it has to be a straight line. So looking at a graph, you can tell without much of a second thought whether a function is a linear function or non-linear function. How about this first one? Is this going to be a non-linear or a linear function? Well, this is going to be non-linear. You see it curves. This is not a straight line. How about this one? Is this going to be a linear or a non-linear function? Well, this is a straight line, so it's going to be linear. How about this one? Is it going to be linear or non-linear? Well, this is also a straight line, so this is going to be linear. How about this one? Is it going to be linear or non-linear? Trick question, right? Remember, we're talking about linear functions versus non-linear functions. Is this even a function? No, this is not a function. It does not pass our vertical line test. So therefore, it is not a linear function. It's not a non-linear function. It's not even a function. So this is not a function. Although it is a straight line, it is a vertical line, and remember, you have to pass our vertical line test in order to be even considered a function. The first part of being a linear function is you have to first be a function. So as long as you have a straight line, not something curved like this, and it is a function, you're going to have a linear function. It doesn't matter if it's straight horizontal or you have something like this. So we already covered the first way in which you're going to be able to identify whether your function is linear or non-linear, and that was by graph. Now we're going to move on to the next one, by function or the model representation. There's only 2 things you're going to have to worry about when you're trying to determine if a function, by looking at its model representation, is linear or non-linear. And the first of those is, the second thing you're going to have to look for is, so those are your 2 things. Your exponent has to be either 0 or 1, and you should be able to get a slope-intercept form out of whatever you're working with here. So let's look at these starting with number 1 and figure out, is it a linear or nonlinear function? So number 1, you see off back that this is going to be a problem. That is a 2 exponent, right? We need to have a 0 or 1. So this is going to be non-linear. How about number 2? Is this going to be linear or non-linear? Well, it seems like our exponent is only 1, right? However, when you try to write this in slope-intercept form, you're going to see you're going to have an issue. You have to get y by itself in slope-intercept form. And when you do that, you get y equals 17 over 3x. Now, is this in slope-intercept form? Not quite. And you also see it violates our number 1 rule. Exponent must be 0 or 1. We know that you can rewrite this as 17 over 3x to the negative 1, right? Anytime you have your variable in the denominator, you can always put it in your numerator by giving it a negative exponent. So this exponent of negative 1 is not 0 or 1. Therefore, this is non-linear. So you see, we have to manipulate that a little bit, but if you realize by getting y by itself, you're going to end up with a negative value in your exponent, you can already write it off as a nonlinear. How about number 3? Is this going to be a linear function or a nonlinear function? Well, if you were to break this up, you can get something like 12, 12, right? And remember your slope-intercept form, I'm going to rewrite it down here, y equals mx plus b. This is your slope-intercept form. Well, you have that, right? You have your m, 7 over 12, and your plus b will be negative 3 over 12. So therefore, you have everything you need for number 2, and you have a 1 in your exponent. So this is a linear function. How about number 4? It seems like you can potentially get slope-intercept form. However, this square root can be rewritten as 28 minus x to the 1/2. Is that 1/2 0 or 1? No. So this is not going to be a linear function. This is non-linear. Number 5. Is this going to be a linear function? Let's take a little bit more space to break this one down. Here we have y equals 100. We have a constant function here. And we want to see, is this constant function, or technically if any constant function, is a linear function or a non-linear function? Notice I have the slope-intercept form written down here so we don't forget it. But I want you to remember, our first 2 components were checking to make sure the exponent was either 0 or 1, and that we can somehow get this slope-intercept form from our equation. So looking at this y equals 100, we can technically derive this in a few different fashions. The first one being, assuming this 100 was your y-intercept, you have y equals sum m for slope times x plus 100. Now, what m or slope would give us this equation up here, y equals 100? Well, we would need m to be 0 in order to cancel out this x here. So we can rewrite this as y equals 0 times x plus 100. And you see that this will go away, resulting in y equals 100. It looks like we can get the slope-intercept form as long as our slope is 0. We already see that the exponent for the x is 1, so it hits both criteria. Thus, we know that our constant function can be considered a linear function. However, there's another way we can write this. Let's say instead of having our y-intercept be 100, let's say our slope was 100. So we have 100 and we have an x here, but instead of having a 1 for the exponent, we have a 0. And our actual intercept, let's say, is 0 here. This, although it doesn't technically look like our traditional constant or what we would think our constant would look like, because the y-intercept is 0 here and we have 100 slope, this will technically give us y equals 100. If we were to simplify everything, we don't have to write that, and we know that x to the 0 is just going to be 1, and anything times 1 is just going to be itself. So this does result in a y equals 100. Once again, this doesn't really fit what we think of a constant function, but mathematically it does give us the same equation. So we have to mention it. Notice our first one does, so we can kind of go with that one and assuming that constant functions are indeed linear functions. So now we covered our first two ways of identifying whether a function is linear or nonlinear. Let's jump into our third way, by points. Now, when I say by points, I mean by points on the graph. We only have the points to work with. We don't have the visual of the graph and we don't have its function. We just have random points and we're going to see, is this a linear function or a nonlinear function? And there's two things for this one that you're also going to have to figure out in order to determine whether it's linear or nonlinear. The first one is you should have more than 2 points. If you only have 2 points, you're not even going to be able to tell if it's a linear function or not. You just don't have enough information to determine linear versus nonlinear. They need to give you at least 3 points. So if you only have 2 points or heck 1 point, there's no way you're going to be able to tell if it is a linear function or not. So that's the first thing. You need at least 3 points. Now, you see here, we don't have more than 3. You can have more. It doesn't hurt to have more than 3 points, but you need at least 3 points in order to tell if your function is linear or not. The second thing, and probably the most important, because once you have at least 3 points, you still need to determine whether it's linear or nonlinear, is you have to have a constant slope. Remember, it's going to look like a line. A line requires a constant slope. So you need to have a constant slope. And remember, when you're dealing with our slope for a linear function, we can also denote that as rise over run. So you need to have a constant rise over run when going from one point to the next point. All of their slopes should be constant, the same exact constant. It shouldn't grow, it shouldn't decrease, it should be the same. So let's look at these 3 examples, taking into account our 2 points up here, and tell whether they are going to be linear or nonlinear. So this first one, we see that we have a -2, 0, and 2 for our x value, and we have an 8, 4, and 8 for our y value. We have at least 3 points here, so we should be able to tell if this is a linear function or not. Let's see the slope. And remember, our slope is going to be our rise over run. So we're going to start here. What is our rise? And our run is going to be 0 minus a -2. Well, what's 4 minus 8? Well, that's going to be a -4. And what's 0 minus a -2? Well, that's going to be a +2. So the answer to that one is going to be a -2 slope, right? When you simplify this, you're going to get a -2 for the slope. So I'm going to put a -2 here. Now we're going to do the same thing for this. What's our rise over run? So rise is going to be, well, starting at 8 now here, right? 8, well, we're finishing at 8 and we started at 4. So 8 minus 4, and our run is going to be 2 minus 0. When we simplify that, we get 4 up top and 2. So our slope in this case is going to be 2. I think we have an issue here. Our slope is not supposed to change. We should have a constant slope. But here we have a -2 and here we have a +2. That means our slope changed. Therefore, these first set of points do not belong to a linear function. This is a nonlinear function. After your first slope change, you don't have to check any more points. So let's say I have more than just these 3 points. Once I see it change once, I can effectively stop there because it doesn't matter if the rest of my graph is going to be linear. If you have a point that's not linear, your entire graph is nonlinear. Let's move on to our second one. We have 2 points here. Oh, already ran into a problem. There's no way I'm going to be able to tell if this is a linear function because I need at least 3 points. So let's say instead of having 2 points here, because you can always just write not enough information, you know, but let's say they did give you enough information. Let's say it was just this, right? 0, 4 was our last point. Now, don't just go writing things in for like homework or a test. If they only give you 2, maybe they want you to tell them that you can't figure it out. But let's say this is our true question. Is this a linear function or a nonlinear function? Let's figure out the slopes. Remember, rise over run. Rise is going to be 3 minus 2 over -5 minus a -10. 3 over 2 is going to give us a 1. And what's -5 minus a -10? Well, this is going to be 5. So going from here to here, you're going to get 1/5. Let's check from here to here. Rise over run tells us we're going to have 4 minus 3 over 0 minus a -5. That's going to be a 1 on top, and 0 minus -5 gives us a +5. So once again, 1/5. Therefore, my slope has not changed. We have at least 3 points now. We are going to say that this second one is going to be a linear function. We have a constant slope. How about our last one? Now, this last one is potentially a little tricky because we're not growing, or we don't necessarily have constant numbers here. This is kind of all over the place. So you might think just by looking at this that this is not a linear function. But remember, these are going to be our two things. We have to have at least 3 points, which we do, and the slope has to be constant. Don't write it off until you figure out whether the slopes are going to be constant. So let's start here. What is the slope here? We have 10 minus 18. Remember, rise over run. And this is going to be 8 minus 2. And this is going to be a -8 over 6. -8 over 6. I'm going to rewrite this right here just to kind of give some space. But -8 over 6. So keep this in our back pocket. We want to make sure that whatever we get next is going to be -8 over 6. So we have this. 6 minus 10 over 11 minus 8. Now this is going to be -4 over, this is 3. Uh-oh. Do we have -8 over 6? Not quite. So you might once again say this is not a linear function because our slope changed. Or did it? This is -4 over 3 and this is -8 over 6. Do we have something in common here? Let's see. -8 over 6 and -4 over 3. I think I can simplify this one. What goes into both of these? 2. So we factor out a 2 or decrease this by 2, whatever you want to call it. And we end up getting something like, so it's going to say that's divided by 2, divided by 2. We get -4 on top, and we get a 3 on bottom. We take out a 2, top and bottom, we get -4 over 3. Well, now what do we have? Do we have the same slope? Yes, we have the same slope. -4 over 3, because we reduced this slope here to -4 over 3, lets us know that this is indeed a linear function. Although our numbers are all over the place, it doesn't matter. As long as the slope is constant, we can say that this is safely going to be a linear function. Linear. So, out of the 3, only our first one was nonlinear. Everything else was linear. And that is how you determine whether your function is going to be a nonlinear or a linear based on points. Now, I know that was a lot to cover today, but I hope you're able to follow all the examples to see your 3 ways in which you can identify your function as either linear or nonlinear. However, if you have any question about what you saw today, or even your own homework, you can always put it in the comment box below, or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. If you haven't done so already, remember to leave a like. It really helps the channel by letting YouTube know that you found this video helpful. And if you found it helpful, so could someone else, your friends. So leave a like, smash the subscribe, hit the notification bell, and while you're at it, share this video. Well, that's all the time I have for today. I'm really hoping this helped with your homework, and I'm looking forward to see you again next week. I'm Courtney, and this has been another session of Tutor Me Sempai.